Okay, so from the Pogel activity, the Bohr model should be not an entirely new concept, but let's go over it. So a long time ago, we talked about Rutherford. He was the one that shot helium nuclei at really like atomic thin layers of gold, and they rarely ever hit anything, which was able to make it so that we can conclude that the electron cloud is actually very widespread and not very dense, and the only dense part of an atom is the nucleus. Okay, so from Rutherford's model, we sat there and thought there was the nucleus and then this single ring of electrons around the outside. But through studies, like our dispersion studies, they are, found that there's got to be more than one level. Okay, whenever we vibrate electrons or give electrons some energy, they drop back down to their standard state with different amounts of energy, giving off different wavelengths, which means that there has to be different levels for them to get to. There's not just one place that the electron stays. Okay? Then this should be kind of clear from the packet, but just to confirm, if the electron is near the nucleus, it has very low energy, it's where it wants to be. If it has been pulled far away from the nucleus, it has high energy. You had to put energy in to get it there. Okay? And this also means that if it falls from here, it's going to give off energy. So, these light spectrums that we've seen and studied a little bit are what led to what is called the quantum model of the atom. Okay? And this has been because light is produced when electrons move. Okay? So when an electron goes up to one level and then falls back down, that's a vibration. And that's what sends the light wave away from it. Okay? So, another thing, and this will be more evident as we continue working with it, but the quantum model of the atom specifically notes that there are certain levels with certain amounts of energy that can be used to get the electron there and then given off when the electron falls. Okay, so it's more like the rungs of a ladder. Rather than if here's your nucleus, the electrons can be randomly anywhere around it. Instead, here's the nucleus, and there's some that can be very close in this ring, and then there's another ring towards the outside, and so forth. Okay, there are specific levels that correlate to an amount of energy given off by the electron. So, Bohr was a scientist that spent quite a bit of time studying this, looking at electron emissions like we have with lots of time and equipment, and came up with the patterns that we found. Okay, so he proposed that there are sets of rings, like planets around the sun, like orbits, around the nucleus of the atom that the electrons can occupy. He also was able to determine that each ring has a certain maximum number of electrons. Okay, so as you go through certain levels, you're able to get more and more spectra emissions from some levels and not others, and that's because there's only a certain number of electrons that can. Okay, so some examples of this is your first energy level, the one closest to the nucleus, can only hold 2 electrons. And then after that, it can only hold 8 electrons. And after that, 18 electrons. If you take a quick look at your periodic table and you sum these numbers up, helium has 2 electrons. Neon has 10. Alright, so the 2 from the first row plus the 8 from the second level. And then above that is and argon has everything added together, so 28 electrons. Okay. One rule that Bohr came up with is that the lower electron levels will be always filled first, for the ground state or natural state of the atom. Okay, in an excited state, things will go into higher levels, so then you might not have everything filled down below. But in the natural, normal state of the electron, without any energy put into it, the electrons will always fill the lowest levels first and then expand outwards. Okay. One last thing as far as a pattern goes with the electron levels. If you get above argon, Bohr came up with this formula to tell you how many electrons there are in each level. Okay, so N stands for the level, so 2 times 1 squared equals 2. 2 times 2 squared is 2 times 4, which equals 8. And then 3 squared is 9 times 2 is 18. Okay, and then if you continue past that, 4 squared is 16 times 2 is going to be 32, and so forth. Okay? So, just an example. The ground state meaning normal state, there's no extra energy in here, nothing's excited. For nitrogen, looks like, if you look at the periodic table, nitrogen is the element right before oxygen. Its atomic number is 7. It has 14 neutrons in its most common isotope. So, when you put those electrons in, you're going to put 2 in the first level, and then there's going to be 5 left, so you put 5 in the next level up, because that hasn't reached 8 yet. Okay, so like oxygen, on the other hand, atomic number 8, 16. In the center, you're going to have your 8 protons, 8 neutrons, and then around that in the first level, you'll have 2 electrons, and then in the second level, there's still 6 more, so you put 6 in. Spread them out as far as you can, because they repel each other, so they will spread out as far as possible. Okay, so Bohr diagram's really easy to draw. Should be pretty simple. Just remember that formula for finding them if you have to go past that third level. Okay, so now when electrons get excited, you put energy into them, they can jump from the level that they're at to something higher. Okay, so for example, if this was an excited nitrogen with its 7 protons and 8, not 8, but it's 7 neutrons. One of those electrons from the ground level might jump to the next level, okay? Which means we'll have 1 in that lowest section. Another one jumps, okay, and then we're going to have the other 5 still left in the upper level. Alright, total we still have 1, 2, 3, 4, 5, 6, 7 electrons. But one of them jumped up to a higher level. Okay, we call that an excited atom. Okay, or the electron has been excited to the next level. It can jump higher than that. It can jump to levels above it that don't have any electrons. This is just a simplification. Okay? So, just some terms to recognize. In order for an electron to make the jump, it must have a specific amount of energy. We call that a quanta. Okay? That's where a quantum model comes from, because the quantum model shows the quanta, or the amount of energy between each level. Okay? Now, if, hypothetically here, because the numbers are way smaller than this, say it takes 2 joules to go up 1 level, then your quanta is 2 joules. Okay? One thing is, if the electron does not have enough quanta, okay, if it doesn't have enough energy to at least equal that quanta, it will not move. It's not going to move halfway between one level or the other. It's either going to stay where it is or go completely to the next level. It's the same thing if you have a little more energy. It's still going to stop at the next level. It won't go to the 1.5 levels up. So the level jumps are only between each level. There's no halfways or anything like that. Okay? So, what happens and why we see these electron emission spectra is because the atoms don't want to stay in those excited states. The electrons want to get back to where they were. They want to get back to the ground state. Okay? Because they're attracted to the nucleus where all that positive charge is. So they don't want to be farther away from it. If they could have it their way, they'd be closer. Okay? So, when that happens, when the electron falls, it's going to give off energy. And in this case, it gives it off as light. It's not heat like the last unit we were on, but it's as light. Okay? Light is another source of energy. So, when you're looking at the colors, okay, that tells you about how big of a jump that was going on. Okay? Big jumps give off the most energy, so it's going to be blue and violet light. Small jumps give off the least amount of energy, so that's going to be mostly your reds. Okay? So, and then just to reiterate something from the packet, every element has its own set of spectral lines. So if you know the set for one of them, you can actually use that to identify it in another compound, in as an unknown, something like that. Okay, so each element has its own spectra. So, to talk a little bit more about light as energy, okay, the frequencies of light dictate different kinds of energies. And I say frequency for a reason because as we get to the equation, frequency is what unit-wise helps us out. Okay, so if you want to find the energy of light, the energy is equal to h, which is a constant called Planck's constant. Okay, he's a scientist that studied this and came up with this crazy number, times the frequency of the wave. Okay? Just so you know, some books, and your book as well, traditionally gives this equation as energy equals Planck's constant times this weird V, because sometimes frequency isn't used as an F. It's as not a normal looking V, but a kind of fancy looking one. I'm not going to use that because I feel like it gets confused with velocity, but just in case you see that, be aware of it. Alright, so Planck's constant is 6.626 times 10 to the negative 31st joules times seconds, not per seconds, but times seconds. And this helps us get the unit we want. Okay, frequency is still measured in hertz. And in case you ever don't know your frequency, remember, we're always going to be dealing with light, so you can use your velocity of light equals the wavelength times frequency, and you can always convert back to frequencies. Say you're given wavelength. Okay? So, a couple sample calculations. So, what is the energy associated with a light wave that has a frequency of 4.57 times 10 to the 21st hertz? So, our equation, so energy is Planck's constant times frequency, and if I plug in what I know, Planck's constant is 6.626 times 10 to the negative 31st joules seconds times 4.57 times 10 to the 21st hertz. Sorry, that should have been for SU. When I solve, I get this number, 2.86 times 10 to the negative 12th. And my units, just like we've been dealing with before, if you're not sure on your units, apply the math that's happening. So we have joules times seconds times hertz, but I can write hertz as 1 over seconds, which means my seconds cancel out, leaving me with joules, which we know is the unit for energy. Okay, so this is a very basic calculation. And then just to give you an idea, one that might work out for wavelength, a sodium streetlight gives off a yellow light that has a wavelength of 589 nanometers. What is the energy of the photon of this light? Okay, so for this one, I want to use this equation, but I don't know frequency. So to find frequency, I'm going to use this. Okay, coming from the fact that the speed of light is equal to frequency times wavelength, I know that frequency has to be the speed of light over wavelength. Okay, so I'm going to have 3.0 times 10 to the 8th meters per second over, and then I'm going to do my conversion down here in this. I have 589 nanometers. 1 nanometer is equal to 1 times 10 to the negative 9th meters. Okay, so I play around with my units. Nanometers are canceling, and then I'm dividing meters per second by meters. So those are going to cancel out too. And that's going to give me approximately this number, 5.09 times 10 to the 14th hertz. Okay, because I'm left with 1 over seconds, which are hertz. Now here, because when I plug this in and in the next equation, everything is multiplication, I shouldn't actually round here yet. But just so that you can get an idea of what number you should be getting there, don't delete it out of the calculator, because you can take it over here to the other equation, and energy is going to be equal to 6.626 times 10 to the negative 34th joule seconds times that number. Okay, and consider it the number that you haven't actually fixed out of the calculator yet. And that's going to give me 3.37 times 10 to the negative 19th. And my units were joule seconds times 1 over seconds. So this 1 over the seconds cancel out again, leaving me with joules. Okay, I know it gets a little complicated when you have more than one equation, but if you just keep track of your numbers and your units, they really aren't that bad. Well, make sure you do the online quiz, and I'll see you in class.